right, I at least want to get a start on this section because it can be a bit of a doozy. So I want to just dive into it. If I need to split it in a couple parts because I don't have a lot of time this morning, I'll do that. As you can see, it's called Rationalizing Denominators and Numerators. So big clue to us that we're dealing with fractions in this section. And just to remind you of something that we now know that we can do when we're dealing with radicals, with roots. If we have like a square root of 2/5, we can break that apart. We can make that the square root of 2 over the square root of 5, and also vice versa. If we're given, let me say, a cube root of 7 over a cube root of 4. When it's convenient, when it serves our purposes, we can make that the cube root of 7/4. So this quotient rule for radicals works in either direction, and we just break it out whenever it serves our purposes, basically. Okay, now that being said, a lot of the time it is, in the book's words, it is helpful. So I really like the way the book says this because it is not necessary, and it's often treated as though it were necessary at this stage in math, and it's really not. It is helpful to write something like what we had here, or what we had here, with no radical in the denominator. Okay. Why is it helpful to write something like one of these expressions with no radical in the denominator? It can make future mathematical calculations easier if we don't have roots down in our denominator. It's easier to deal with common denominators, for example, to create common denominators if we have whole numbers in a denominator, not roots. So I'm just going to say it's easier to add or subtract fractions just because I feel like if we're going to state that something is helpful, it's good to kind of know why. Another thing, another reason that it's helpful, or I guess historically that this kind of process originated, I can't remember what book I got this from. But recall that fractions are actually division problems, are actually little division problems. We don't usually work them out as such. But that fraction notation is another way of indicating that a division is being set up. So let's just make one up here. Consider 2 over the square root of 2. Okay. In a calculator, And I realize, of course, I probably don't have any such thing as a calculator running around. Let me go grab my phone. That'll be as close as we can come.
Mama, what did you got?
Just my phone.
Mama.
Okay. I'm the worst at trying to use the functions in my own calculator. Okay, so if you use a calculator to approximate the square root of 2, because it's one of these numbers that can't, it's not like the square root of 4 that comes out nice as a whole number. You get something like this: 4, 1, 4, 2, 1, 3, 5, 4, 6, 2, and so on. So look at what you are, look what you're basically saying about this division problem. It's 2. And if you turn that into a division problem format, wow, I'm probably going to want to do that down here. Back in the days before calculators made this sort of thing easy, think about how we would have to do this. We would have to move this decimal point over 1, 2, 3, 4, 5, 6, 7, 8, 9 times, and then add 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. This would be the sort of division problem we were having to work out prior to the days of calculators. Really hard division prior to calculators. So back when the best they could do was approximate one of these square roots, because now you just, in your calculator, you could type in 2 divided by the square root of 2, no approximation needed, and it will spit out the result. On the other hand, but if the square root is in the numerator instead of the denominator, so let me just make a totally different problem. So the square root of 7 over 4, that's approximately equal. If I grab my calculator, again, they probably would have back in the day used tables of approximations to do this. It was on my phone. Did you know that, Matthew? Did you know you were on my phone? I think I left it in the office.
Wow.
Oh, I forgot it the other day. So you've got this over 4. This translates more naturally. If you have to do this type of division, and the approximated long, ugly decimal value is actually inside the division sign, you can dive right in. You don't have to move decimal points over. You can dive right into the division. 6 times 4 is 24, and you're just getting right into right down into the business much easier. Okay, so that's another reason I've seen it explain why do we prefer there not to be square roots or cube roots or any other kind of root in a denominator. Now the book is going to actually give us some scenarios where we're okay with the root in a denominator, but we don't want one in the numerator. And there, I think they're just playing with us. I don't know of any historical background for making a root disappear in a numerator. It's all been focused usually on the denominator. So if you're in algebra, trigonometry, pre-calculus, that sort of era of math, a lot of times your teacher is going to require you to give answers with the denominator rationalized, meaning with no roots in the denominator. You get farther up into calculus and stuff, a lot of times your teacher stops caring, and it can feel a little bit jarring because in algebra it's treated almost like the 10 Commandments, like you must rationalize your denominators. And then a lot of times in calculus, it's like hands off, everything's very clean. So I really like, yeah, the 10 Commandments. So I really like how our textbook here uses the word helpful. A lot of times it's helpful to get rid of radicals in the denominator, but it's not necessary. So kudos to this author, Elaine. So let's just dive into an example of how to rationalize. So that means to get rid of the root. Okay, so recall this type of a fact. The square root of 3, for example, times the square root of 3 equals 3. And there's a couple ways you can see that. You can go ahead and recognize that 2 square roots of the same quantity become that quantity, or you can sort of go square root of 3 times the square root of 3 is the square root of 3 squared. Remember that little invisible 2? Okay. And then you can convert into all that exponent notation like that. Multiply out your 2 and your 1/2 and just get 3. A couple of different ways you can look at that. Be quiet. So this is what we're going to be relying on, that piece of information. So in the first practice problem, number 72, we've got something like this, which again, in calculus, they'd probably be like, who cares? In algebra, on up through trigonometry, teacher might make a little bit of an issue, rationalize your denominator, maybe take off moderate amount of point value. Okay, so what we're going to do is we are going to multiply this fraction by 1. That is all we're going to do, because that's legal, right? We do this all the time in math. We multiply things by the number 1, but we choose to cleverly disguise the way that that number 1 appears. Look at that. 1 is now the square root of 3 over the square root of 3. Okay, what that means is in the denominator, we now have 3 itself. In the numerator, we have something that looks messier than what we had, but that's okay. It doesn't matter. Because the mess is up top, and that's considered okay algebraically. They just don't want to have the mess in the denominator. No, that's not your chair. Your chair is over there. Right? You can sit in your chair. Not right now. I'm busy. Okay. Okay. Let's try another one. That was a very simple example. This one is good for expressing an idea that we don't want to get too far down the road before we lock into our memories. And I'm going to put it up here. It didn't apply in part A. And I'm just going to say, try to simplify all roots before you worry about, probably don't need, okay, before worrying about rationalizing. Okay. Sometimes you can save yourself a lot of work if your square roots will actually simplify themselves away with no extra work needed. So for example, I can see this square root of 25 turns very nicely into a 5. And even though it's in the numerator and we're focused on the denominator, let's see, I didn't get the directions in here, did I? We just dove right in, rationalize denominators. So that's what we're doing. So even though the square root of 25 is in the numerator, it's a good example of how if you recognize a root that can be simplified, might as well go ahead and do it. Okay, down here, we can say square root of 4 times the square root of x. Just go ahead and take advantage of one of our rules for roots. Great. Is the block still over there? So we've got 15, about 2, square root of x. Now would be the time when we could think about if 15 over 2 reduced. Well, it doesn't. But, you know, if it did, we would go ahead and reduce it. And so we're left with this square root of x, and that's going to become the focus of the rest of the problem. So now is where we break out our new technique. We go like that. So create that cleverly disguised number 1. 15 square root of x over 2. And then remember that these two matching square roots are going to come together. And we've got that, which is considered prettier, nicer, equal in some people's eyes. Preferable at the very least. Okay, now here, they're throwing us a cube root, and cube roots, I'm just going to go ahead and tell you, cube roots, fourth roots mess everything up. Okay, so before I even wade into this, let's consider this. The cube root of 5, for example, times the cube root of 5 is not enough to release that 5 on the inside. The way it worked for square roots, not the way it's going to work for cube roots. You need 3 of those cube roots. Cube root of 5 times cube root of 5 times cube root of 5 to equal 5. And in parentheses, one reason for that. That's the cube root of 5 cubed. You know, if you bring those together, 5 times 5 times 5 equals 5. 1/3 equals 5. Okay, so basically you need 3 of these guys. Okay, now another way to think about this another way to write what I just had up here all spread out, or what I then brought together like that, is what follows. And this is going to feel totally arbitrary, but there's a method to my madness. I could write it like that. one of the 5s pulled off to the front and 2 of them left behind, or 2 of them pulled to the front, 1 of them left behind. This is just giving us options, and we're going to select from those options how to write this expression or which way to focus on this expression as we dive into this problem. So let me bring back down the cube root of 2 over 9. So the cube root of 2 over 9, we know for starters, we want to break this guy up. Use that quotient rule like that. Now, 9, classic sort of temptation at this point is to focus on 9 and think, okay, well, I had a 5 here. I needed 3 cube roots of 5. I need 3 cube roots of 9. But consider the fact that 9 is something to a power already. This is where, man, the cube roots just sneak up on you. Yeah, did you ever find it? We've got that. Okay, so we've already got like something to the 2nd power. In order to be able to clear out our cube root, we need something to the 3rd power. So in a case of let's just multiply by what's missing. What's missing is just that extra cube root of 3, because there's 2 of them. There's 1 more of them. Put them all together, you would have the ability to release your bottom expression there from the square root. I'm sorry, from the cube root. Okay, so up top we have the cube root of 2 times 3. If I bring them together, that's turned into a cube of 6. Down below, I've got the cube root of 3 cubed. Good news there. It's just a 3. Okay. Turns into a 6. So man, the jump from square roots to cube roots, and as you might imagine, from cube roots to 4th roots or higher, it's a pretty significant jump. You have to really be thinking on multiple levels at once. Okay, let me see here. Making sure they don't skip too many or jump too far ahead. Just one practice problem down the page. I'm just checking their method here in the example, because sometimes they surprise me how far they jump between examples. Okay, so we're still rationalizing the denominator. We've got one giant thing here. Now, looking at everything that's on the inside, I'm seeing sort of an already simplified quantity. So I'm not seeing square roots of 25 or square roots of 4 in there, that sort of thing. So I can go ahead and break this apart. Okay. And there's really, in a way, no reason for me to separate out my square root of 5, my square root of y, because they can't be simplified. So what I can do relative to simplifying, if I'm going to multiply by 1 here, I'm just going to disguise that 1 like this. Okay, just kind of go for it. Okay, so on the bottom, I know that these 2 matching square roots will release that inner quantity. And then up top, everything being multiplied together, 3 times 5 is 15. You have a y and a z, and you'll see the book just opt for alphabetical order. It's just what they do. Okay. So simpler in a way than the cube root problem we just worked. It's just that they were trying to mess with their mind with the inclusion of the so many numbers of variables in the same problem. So moving ahead to practice problem 3. All right, now this beauty, back to the cube roots. And I am seeing a cube root on the bottom that can be simplified. Okay, now up top, I recognize that the kind of root it is, the index, as they would say, the 3, is smaller than the 2. So I'm not going to find, there's not at least 3 z's hidden under this top root for me to simplify. But on the bottom, let me break this apart. If I choose to treat this as the cube root of 27 times the cube root of x to the 4th, well, for one thing, 27 is in and of itself a perfect cube. That's great news. X to the 4th, if I have 4 x's, because x to the 4th is as follows, I certainly have 3 x's hidden under that root. So I'm going to be able to simplify a little bit what I've got going on there. So as I stated earlier, do all of that simplification prior to worrying about how deep you have to get into the rationalizing. So cube root of 27, that's just 3. And cube root of, maybe been a little while, or just it's never a bad time to do a little bit of review. So we're breaking apart by the product rule for exponents. We multiplied x cubed times x to the 1st. We would add their powers. We would get back the 4. Okay, let me further break this apart. So we're slowly but surely simplifying this thing down. So 3 cube root of 27, and then the cube root of x cubed. So you've got matching index, matching power. That's just an x. We don't have to worry about absolute value of x for one thing with cube roots or fifth roots, any odd numbered root. But previously, in the middle of section 8.4, they snuck it in on us that basically you don't have to worry about that anyway, because they've chosen to let all the x's always represent positive numbers. So I stated that. It's worth bringing up every now and then, even though it's nothing that they want us worrying about at this phase, but it is something, a mathematical thing that we would have to consider at a higher level. Okay, here's where we're sitting right at the point where it's time to start thinking about rationalizing. Okay, so notice the problem here, the focus. The rest of this practice is going to be the fact that we have a cube root of x stuck down there. It's a cube root of x to the 1st. And in order to remove this final cube root in the denominator, we would need exactly what we have here, cube root of x cubed. That's what we need. So we've got one of these x's under cube root. We need 2 more. So let's just form our fraction equal to 1 as follows. Okay. And underneath, that'll give us 3x, another cube root now of x cubed, which we'll be able to remove. Up top, cube root, it looks like of x squared z squared, or z squared x squared, if you prefer to go with the order, the first order that you see. Okay, so Yeah. Okay, and then you've got now an extra x. Okay, over 3x squared. And that's, I say that's it, like it wasn't a hard process at all. It's pretty involved. I am going to pause right there because the section 8.5 right there takes a pretty severe swerve into some more complex territory. So this is going to be my introductory video. And then we're going to go make some breakfast here. And later on, maybe it could be next week, who knows, but I will finish 8.5. But this is just sort of like the basics. And then we'll take it up a notch in our next recording.